Now, by using Peugeot's curves, we have found the moment coefficients m1 and m2. m1 is equal to 8.5 into 10 raised power minus 2 and m2 is equal to 0.9 into 10 raised power minus 2. हमने कौन सा curve use किया? We used the curves for k is equal to 0.4 and we had the u by b ratio and b by l ratio. So उसके हिसाब से हमने m1 and m2 calculate किया. These are our moment coefficients and this will give us bending moments along the long span and along the short span. First, bending moment along short span as per the Peugeot's theory is given as my short span is my, here in the diagram you can see this is my short span breadth 1.875 and this is my long span length 5 meters. All right, so I'm calculating bending moment along my short span, which is 1.875 meters, using Peugeot's theory, and the equation is by which I can calculate it is mb is equal to w m1 plus 0.15 m2. All right, so let us calculate, wherein this 0.15, this is the Poisson's ratio, lateral strain by longitudinal strain, already discussed. And for reinforced concrete, it is taken as 0.15. All right, now let's calculate the bending moments along both the spans, the short span and along the long span. We have taken the values from Peugeot's curves for the relevant values of u by b, v by l, and for k is equal to 0.4. I have my moment coefficients. Now, mb, this is the bending moment along shorter span. क्या है formula? W m1 plus 0.15 times m2. Now this W, this is the load from the wheel under consideration, and for one track it is, this is 750 divided by 2 in case of class AA loads for tracked vehicle, RC class AA loads tracked vehicle, and this is equal to 350 kilonewton. All right, so MB is 350. My value of M1 from my curve is 8.5 into 10 raised power minus 2, so it is 0.085 plus 0.15 times M2 from my curve is 0.9 into 10 raised power minus 2, so it is 0.009. By calculations, bending moment along short span or along breadth is equal to 30.1 kilonewton meter. All right, this is my bending moment from the live load along the shorter span. In the similar manner, I'll calculate my bending moment along the long span, ML. As per M. Peugeot's theory, it is W M2 plus 0.15 times M1. But before that, let's apply the, as you know, the slab is continuous. As the slab is continuous, so I'll be applying both impact factors as well as continuity factors. You know, for impact factor, we have already discussed that impact factor we are taking as 25%, and continuity, to allow for continuity, you know, we multiply any bending moment by 0.8. All right, so as my slab is continuous, let me apply both the factors to my bending moment along the shorter span. So it will be equal to, after applying both impact factors as well as the continuity. First, impact factor, how much is it? 25%, so it will be 1.25. Multiply by, to allow for continuity, we multiply every bending moment by 0.8, and what is the bending moment? 30.1. So it will be equal to 30 point, by calculations, 1 kilonewton meter, after applying both impact factors and continuity factors. You may write here applying impact and continuity factors. All right, bending moment along the short span is 30.1 kilonewton meter. All right, bending moment along long span, ml. How much is my W? It's 350. M2, 0.009 plus 0.15 times 0.15 is the Poisson's ratio, and M1 is how much? It is 0.085. By calculations, my ML, that is my bending moment along the longer span, is equal to 7.61 kilonewton meter. All right, before proceeding, let me rub it first. So I'm calculating my bending moment along the shorter and the longer span that is caused by the IRC Class AA tracked vehicle live loads. And now I calculated my bending moment along the longer span, which is equal to 7.61 kilonewton meter. अब मैं इस पे भी apply करूँगी अपना impact factor और continuity factor. Applying impact and continuity factors. Applying impact and continuity factors to my bending moment along the longer span, it is 1.25 into 0.8 to allow for continuity. Slab is continuous, and how much was the value? 7.61. So by calculations, it is equal to 7.61 kilonewton meter. Value remains same because we multiplied by these two factors, so the values are same. All right, now I used Empedur's theory and I got my bending moments both along the longer span and along the shorter span. Now I will calculate the same moments but by dead load this time. All right, dead load bending moment. This is my next step, dead load bending moment. These were the moments caused by the live loads. Now I'll calculate the dead load bending moment. First, I have to calculate total load on panel. Since हमने एक इंटीरियर डेक स्लैब पैनल ही लिया था, उसी को हम डिज़ाइन कर रहे हैं अपनी डेक स्लैब को डिज़ाइन करने के लिए. फर्स्ट मुझे कैलकुलेट करना है टोटल लोड ऑन पैनल. अभी हमने लोड किया था डेड लोड ऑन पैन स्लैब. कितना आया था वो इनिशियली जो किया था by calculating the dead weight of both the slab as well as the bearing core, that was 7.0 kilonewton per meter square. All right, now I'll calculate total load on panel कितना बनता है. टोटल लोड ऑन पैनल है, डायमेंशंस को मल्टीप्लाई करेंगे इस लोड के साथ, तो वो एक पैनल पे वो इतना लोड बनेगा. मेरे एक पैनल का की डायमेंशंस क्या है? ब्रेड्थ है 1.875 और लेंथ है 5 मीटर्स. सो मेरा टोटल लोड ऑन पैनल है लेंथ मल्टीप्लाइड बाय ब्रेड्थ मल्टीप्लाइड बाय द डेड लोड जितना आया था. दैट इज द टोटल डेड लोड ऑन माई पैनल. माई लेंथ इज 5, my breadth is 1.875 meters and the dead load जो already हमने initially calculate सबसे पहले वही calculate कर रखा था, it is 7.0. So by calculations my total load on panel is 65.6 kilonewtons. All right, this is my total load on panel. All right, अब मुझे निकालने हैं moment coefficients. कैसे करते हैं? Let me rub it first. All right. I'm calculating my dead load bending moments along both shorter as well as the longer span. When one wheel is of full size of the panel, live loads को calculate करने के लिए we're assuming that one wheel is at the center of the panel. Now for dead load calculations I'm assuming that when one wheel is of full size of panel, जब एक wheel इस पूरे panel के size का होगा तब उस time क्या होगा? U बराबर होगा B के, and V will be equal to L. When one wheel will be of the full size of the panel of this panel, then U will be equal to B and V will be equal to L. All right, and that means U by B ratio, that will be and 1, and V by L ratio, that will also be equal to 1. When one wheel is of full size of the panel, then U is equal to B. जब ये पूरा साइज होगा किसके, एक पैनल के ही साइज का, जो मेरा इंटीरियर डेस्क स्लैब पैनल है, तब U B के बराबर आएगा और V L के बराबर. सो मेरे रैशियोज U by B it's 1 and V by L वो भी 1 हो जाएगा. बट K का वैल्यू ऑलरेडी है. द K इज द रेशियो बिटवीन शॉर्ट स्पैन एंड द लॉन्गर स्पैन. वो हमने ऑलरेडी कैलकुलेट किया है. ब्रेड्थ बाय लेंथ, बिकॉज ब्रेड्थ इज माई शॉर्टर स्पैन एंड लेंथ इज माई लॉन्गर स्पैन. इट इज इक्वल टू 0.375, which I approximated to 0.4, and 1 by K is 2.66. So this time I'll be using M. Peters curves for the ratios. Listen carefully. U by B1, V by L1, and K 0.4, and 1 by K 2.66. I'll use the curves for these ratios to calculate my moment coefficients M1 and M2. By using the Peters curves, my M1 is equal to 0.045, and by M2 it is equal to 0.004. All right. This time I'm using the M. Peters curves for the ratios. U by B is equal to 1, V by L is equal to 1, and K is equal to 0.4, and this thing 1 by K is equal to 2.66. उसके हिसाब से कर्व से मेरे मोमेंट कोफिशिएंट्स का वैल्यू आता है M1 is equal to 0.045 and M2 is equal to 0.004. ये तब हुआ जब मैंने बोला कि when one wheel is of the full size of the panel, तब U B के बराबर आ गया और V L के बराबर, और ये रेशियोज दोनों यूनिटी आ गए. अब इन्हीं कर्व्स को यूज करके for U by B1, V by L1, and K 0.4, I use the curves for K is equal to 0.4. Then I calculated moment coefficients for these ratios U by B1 and V by L1, and the ratios or the moment coefficients are these. M1 is equal to 0.00045 and M2 is equal to 0.004. Now I'll calculate my bending moments. This is from Peters or Peters, howsoever you may like to pronounce it, curves. All right. Now bending moment along the shorter span. Now this time the formula is same, obviously M1 plus 0.15 M2. But what will change this time? When I calculated for live load, W was 350 for RC class A8 tracked vehicle. One track, the wheel load on the one track will be 350 kilonewtons. But this time, I'm calculating the dead load bending moment. So this W is how much total load on the panel? Total dead load on the panel, 65.6 kilonewton. All right, and not 350, because that was for the live load and this is for the dead load. So let's calculate the bending moments along the shorter span. Now W this time is 65.6. M1 I calculated from my curves. It is how much? 0.045 plus 0.15, the Poisson's ratio, into M2, it is 0.004. By calculations, my MB is equal to, it is equal to 3 kilonewton meter. All right. My MB is equal to 3 kilonewton meter. Let me rub it first and then we'll be moving further. Now I have to apply continuity factor. Live load ke time we were applying both the factors, continuity as well as impact. But this time Since this is the dead load bending moment calculations, I'm not applying impact factors. Impact तो सिर्फ live load की वजह से ही है. So only continuity factor to allow for continuity. Taking continuity factor or applying continuity factor, my bending moment along the shorter span by the dead load is equal to, अभी calculation से आया था कितना, 3 kilonewton meter. So to allow for continuity, I have to multiply my bending moment with 0.8. So it is 0.8 into 3, and this is equal to 2.4 kilonewton meter. All right. Once again, I'm saying that I'm applying only continuity factor to calculate my dead load moments, bending moments, and not the impact factor. That is because of लाइव लोड, और वो हम लेते हैं सिर्फ लाइव लोड्स में. डेड लोड्स में सिर्फ कॉन्टिन्यूटी फैक्टर, लाइव लोड्स में दोनों कॉन्टिन्यूटी एज वेल एज इम्पैक्ट. ऑलराइट, नाउ आई विल कैलकुलेट माय बेंडिंग मोमेंट अलोंग द लॉन्गेस्ट स्पैन. लॉन्ग स्पैन, उसको आप शॉर्ट स्पैन भी लिख सकते हैं ऐसे, एम बी को. इट इज बाय एम पीजर्स थ्योरी, m2 plus 0.15 m1, and my W is 6 total load on the panel, 65.6. My M2 is 0.004 plus 0.15 times. My M1 is how much? It is 0.045. So by calculations, my ML is equal to 0.656 kilonewton meter. Then after, I have to apply continuity factor, applying continuity factor, my bending moment along the longest span is 0.8 into 0.656. So by calculations, my ML is equal to 0.53 kilonewton meter. All right, so I calculated both bending moments due to live load along both the spans and bending moments due to dead load along both the spans. Now let's add them to take our design moments into consideration. All right. Total design moments along width and length of the panel. MB and ML. All right. This is the summation of the bending moment along the shorter span, first due to live load and then due to dead load. Live load से कितना आया था? 30.1 और dead load से 2.4. So it is 32.5 kilonewton meter. All right. In the same way, bending moment along the longest span, live load से कितना आया था? 7.61 and dead load से 0.53. 8.14 kilonewton meter. So these are my design moments. This is a long design moment along the shorter span, and this is the design moment along the longer span. All right. इसके बाद reinforcement पे जाना है. Reinforcement details or reinforcement. All right. उसके लिए sigma CBC, sigma ST and elastic design coefficients को देखना होता है. उसके बाद effective depth वगैरह and reinforcement details will be calculated. Now, what are these elastic design coefficients? Since this is working stress method of the designing of the bridges and this is not the limit state method, so हमें elastic design coefficients लेने हैं. अब ये elastic design coefficients क्या होते हैं? Currently, we are using only elastic design is used in bridge engineering. दो हम अब limit state method से भी देख सकते हैं, but for this example, I am taking this working stress method into consideration. And this is because the effects of dynamic loads on the performance characteristics of structures proportioned according to ultimate strength design methods were not fully understood. A behavior in designing a bridge and the effects of the dynamic loads, because it is subjected to dynamic loading. Bridges are always subjected to dynamic loadings. Till the time the effects of the dynamic loads on the performance characteristics of structures proportioned according to the ultimate strength design methods were not known, till that time we were using the elastic design method. And for that method, we have to take some elastic design coefficients. Now, in the design of the reinforced concrete one-way slab or a two-way slab or a singly reinforced beam, we have to compute the design coefficients, and they are M, N, J, and R for any given set of values of sigma CBC and sigma ST. All right, and these are known as elastic design coefficients. M, N, J, and R. Some books write Q instead of R, and some write R, so it's one and the same thing. And these are the elastic design coefficients for a given set of values of sigma CBC and sigma ST, where sigma CBC, you know, is the permissible stress in concrete, and this is the permissible stresses in, these are the permissible stresses in the steel. All right, and M is the modular ratio. M is the modular ratio. N is the ratio of the depth from the extreme compression fiber to the neutral axis. J is known as the lever arm factor. And R is the coefficient of resistance. Let me rub it first and I'll tell you in detail about the reinforcement and about my elastic design coefficients. Reinforcement. Sigma CBC, permissible stresses in concrete, and the permissible sigma ST, permissible stresses in the steel. My elastic coefficients M, N, J, and R or Q. Some books write it like this. All right, M is the modular ratio. And we have these elastic design coefficients for any given set of values of sigma CBC and sigma ST. And we take them from the tables as given by the relevant codes. This is the modular ratio. M is the modular ratio. Then we have N, which is the ratio of depth from the extreme compression fiber, extreme compression fiber to neutral axis. J is my lever arm factor, and R is my coefficient of resistance. It is coefficient of resistance, which when multiplied by the BD square gives me moment of resistance. If I multiply my coefficient of resistance by BD square, I'll be having my moment of resistance. And as per IRC 21, my modular ratio, or we usually take modular ratio as 10. All right. So this was about the elastic design coefficients, which we use for calculating our reinforcement details and effective depths, etc. And I have my elastic design coefficients M, N, J, and R for a given set of values of sigma CBC and sigma ST. And for or as per IRC 21, we take M, or the modular ratio, as 10. Now, क्वेश्चन के डेटा में ही दिया गया था that you have to use M25 grade of concrete and Fe415 bars. IRC tables के हिसाब से मेरे सारे वैल्यूज अवेलेबल है. M तो खैर 10 ही लेते, M, N, J and R, जिसको कुछ बुक्स QB लिखती है. सिग्मा CBC for these values. अब ये वैल्यूज कहाँ से मिलते हैं? These are from the tables of IRC. वहाँ पे आप you have to check for your grade of concrete and for your grade of steel. Since question के data में ही बोला गया था you have to use M25 for concrete and Fe415 HYSD bars. So from tables, I'll be having the values of everything. My sigma CBC from the tables, it is 8.33 Newton per mm square. Sigma ST is 200 Newton per mm square. M, as per IRC 21, we take 10. N is 0.29. J, my lever arm factor, is 0.90. And my moment coefficient of resistance, R, which when multiplied by BD square will give me moment of resistance. So my coefficient of resistance is how much? As per the tables, it is 1.10. ये सारे values हमें मिल जाते हैं tables में जो IRC ने दिए गए हैं, codes में होते हैं. हमने देखा values किन के लिए? M25 grade of concrete के लिए और Fe415 HYSD bars के लिए. उससे मेरे ये सारे values table से मैंने calculate किए. Tables में already दिए होते हैं. You just have to see for which category of the grade of concrete and the grade of steel you are using, then you'll be having all these values. इसके बाद I have to calculate effective depth required. Whose effective depth required? Because I have assumed I'm designing my slab, I have assumed कि मैं 200 mm ले रही हूँ. अब I have to check whether this is alright or wrong. So we are calculating that. Let me rub it first. Effective depth required is given as all right, and this is the moment, and this is the moment along the shorter span. That is how much? 32.5 kilonewton meter. I'll multiply by 10 raised power 6 to allow for dimensional homogeneity. Very important. R कितना है? 1.10 from the tables. उसके बाद breadth. Slab का हम ले रहे हैं 1 meter breadth, so 1000. By calculations, this is equal to 172 mm. That means 172 mm is the effective depth required. इसके बाद step by step I have to first assume clear car. If I'll assume clear cover to the reinforcement 20 mm and dia of bars, जो मैं लगाऊंगी dia of bars to be used 12 mm. All right, I'm assuming my clear car to the reinforcement as 20 mm and the dia of bars as 12 mm. All right. Then what will be the effective depth? How much will be the effective depth? Effective depth will be total depth जितनी मैंने assume की है minus clear car and minus die of bars that I am using divided by 2. So this is 200 minus 20. Since I assume that I'll be using 12 mm dia bars, so it is minus 6. And this by calculations is 174 mm. Alright. यहाँ पे मैंने clear cover assume किया है 20 mm और die of bars किया 12 mm assume. उससे हिसाब से effective depth जो provide की गई है वो बनती है 200 minus 20 minus 6. अगर मैंने क्लियर कार के जगह इफेक्टिव कवर लिया होता देन मुझे 5/2 इससे सब्ट्रैक्ट नहीं करना था. सिंस मैंने क्लियर कवर लिया सो 200 minus 20 minus 5/2. For example, if I would have assumed effective cover as 20 mm, तो इफेक्टिव डेप्थ प्रोवाइडेड होता है 200 minus 20. अब प्लीज़ कंफ्यूज मत होइएगा, कुछ बुक्स ने अगर ऐसे किया होगा या आप कभी कंफ्यूज हो कि इन वन सिचुएशन वी डोंट सब्ट्रैक्ट दिस थिंग एंड इन अदर situation we do subtract this thing. How does this arise? This is because here I'm assuming clear cover as 20 mm, then I have to subtract the dia by 2 to get my effective depth. If instead of clear cover I would have assumed effective cover, then my effective depth would have been 200 minus 20, and there was no need of subtracting this thing from the dimensions. All right, but since I assumed clear car, I hope the difference between clear car and effective car is known to you. All right, so effective depth provided is 174 mm. Hence provision of total depth, this was effective depth to be provided. All right, hence provision of total depth of 200 mm is safe. All right, हमने कितना रखा प्रोविजन ऑफ टोटल डेप्थ 200 mm, और हमें कैलकुलेशंस के हिसाब से या जितने भी हमारे बेंडिंग मोमेंट्स जो हमने कैलकुलेट किए उसके हिसाब से हमें कितना इफेक्टिव डेप्थ प्रोवाइड करना था 174 mm एज पर द क्लियर कार जो मैंने अज्यूम किया और द डाया ऑफ द बार्स जो मैं यूज़ कर रही हूँ वो इतना था, लेकिन मैंने कितना रखा है 200 mm. हेंस दिस इज सेफ. इसके बाद रीइंफोर्समेंट. एरिया ऑफ main reinforcement. Main reinforcement is along the shorter span. Area of main reinforcement is equal to MB divided by sigma ST multiplied by J lever arm factor multiplied by D. Alright, अब मैं पहले इसको रब करती हूँ, then we'll proceed further. So area of main reinforcement, area of main reinforcement how much? Area of main reinforcement is equal to MB along the shorter span sigma ST multiplied by J and multiplied by D. Now step by step, how much is my MB? It is 32.5. 32.5. How much is sigma ST? As per the grades already calculated from the table, 200. J lever arm factor 0.94 multiplied by D. अब effective depth shorter span से हमने calculate की कितनी थी 174 to allow for dimensional homogeneity, I have to multiply it by 10 raised power 6 so that units बराबर आए हर जगह. And by calculation, it is 1037.67 mm square. This is the area of main reinforcement required, and I will be using 12 mm dia bars as already stated. Adopt 12 mm dia bars. How much is the area of one bar? It is pi by 4 into 12 square of it, that is 113.04 mm square. Now how much, therefore number of bars, कितने bars हमें चाहिए? 1037.67 जो कि है मेरा एरिया ऑफ मेन रीइंफोर्समेंट, जो कि मुझे लगाना है. जबकि मैंने अज्यूम किया मैं 12 mm बार्स यूज करूंगी, उसके एक बार का इतना है एरिया. सो नंबर ऑफ बार्स इज 9.17. So approximately I'll be going with 10 bars. Alright. अगर मैंने 10 bars लिए तो AST provided कितना रखा मैंने? Obviously 10 multiplied by the area of 1, which is 1130.4 mm square. Required was this, I provided this, hence safe. Now after that I have to calculate at what spacing I'll be using these bars. Spacing between the bars कैसे calculate करते हैं? Area of 1 divided by AST provided multiplied by the B. So area of 113.04 divided by provide कितना किया मैंने AST 1130.4 multiplied by breadth, which is 1000 or 1 meter or 1000 mm, and by calculation it is 100 mm. All right, so spacing between the bars is 100 mm. So I'll write provide 10 bars, provide 10 bars of 12 mm dia at the rate of 100 mm center to center along with span, short span. All right, इसके बाद I'll calculate, this was area of main reinforcement, area of longitudinal reinforcement, that is along the longer span. All right, area of longitudinal reinforcement, area of longitudinal reinforcement is how much? It is ml divided by sigma st into j into effective depth but along the longer span. That is equal to how much? Now first we have to calculate this. It is effective depth along the shorter span 174 minus the bars I'm using. I use a 12 mm bar, so एक side से 5 by 2, 5 by 2. So DL 162 mm. To calculate area of reinforcement along the main span, along the shorter span, that is my main reinforcement. This is to be noted by the students that along the shorter span, my main reinforcement is along that. That was the area of main reinforcement. And to calculate area of longitudinal reinforcement, that is along the longer spans, you have to take care of effective length, effective depths along both the sides and the corresponding bending moments. Bending moments तो आपके पास होते ही है, shorter span के लिए भी, longer span के लिए भी, और effective depths का ख्याल रखना पड़ता है both directions में, shorter spans में भी और longer spans में. Shorter spans में हमने देखा कि effective depth जो थी वो थी जो हमने कैलकुलेट की बाय दिस वाज माय अज्यूम डेप्थ माइनस क्लियर कवर जो मैंने रखा और माइनस डाई ऑफ बार्स में मैंने पहले ही बोला था मैं 12 mm की लगाऊंगी तो 5/2 सो विच केम इक्वलेंट टू 174. अब लॉन्गर स्पैन के लिए इफेक्टिव डेप्थ बनती है एक तो 174 लेकिन इससे सब्ट्रैक्ट करना है दोनों साइड्स का बार्स मैंने वहां से कितने लगाए थे 12 mm के तो एक साइड का 5/2 एंड दूसरी साइड का 5/2 which by calculations is equal to 172 mm and students please note this कि इसमें गड़बड़ ना हो अगर इसमें गड़बड़ होगी तो आपकी जो एरिया ऑफ रीइंफोर्समेंट अलोंग द मेन जो मेन रीइंफोर्समेंट है और जो एरिया है लॉन्गिट्यूडनल रीइंफोर्समेंट का वो वैल्यूज आपके गलत आएंगे सो इन बातों का खास ध्यान रखिएगा that what effective depths you are using to calculate your area of main reinforcement and to calculate your area of longitudinal reinforcement and the corresponding bending moments वो तो है ही main reinforcement के लिए it is bending moment along the shorter span and longitudinal reinforcement के लिए it's the bending moment along the longer span इन बातों का ख्याल रखिए बाकी it's all very easy all right let's move on so how much is my GL, it's 162. Now let's calculate my area of longitudinal reinforcement in the same or on the same lines as we calculated the area of main reinforcement. That was the area of reinforcement required along the shorter span. All right. So how much is my area of longitudinal reinforcement? Area of longitudinal reinforcement is area of longitudinal reinforcement is ml divided by sigma st multiplied with the lever arm factor multiplied with the effective depth along the span. ml as calculated 8.14 divided by sigma st from the tables 200 lever arm factor 0.90 and effective depth abhi dekha humne 162 10 raised power 6 by calculations this is equal to 279.14 mm square. This is the area of the longitudinal reinforcement required. I'll be assuming or I'll be adopting rather the same 12 mm dia bars. 10 भी लगा सकती थी but let's suppose we are adopting 12 mm dia bars. Area of one bar, how much? Pi by 4 into 12 square, it is 113.04 mm square. Number of bars, area of reinforcement that is required, this one 279.14 divided by area of one bar 113.04 multiplied by and this is equal to 2.46 or I'll be saying approximately let's suppose we are using 3 bars. All right, so how much is my number of bars? जितना मेरा ज़रूरत था एरिया ऑफ लॉन्गिट्यूडनल रीइंफोर्समेंट कितना ज़रूरत है 279.14 और हमने अडॉप्ट किए 12 mm डाया बार्स और एक बार का इतना एरिया है so this divided by this will give me the number of bars which came equal to 2.46 so let's assume or let's adopt that we'll be using 3 bars. अब AST हमें प्रोवाइड कितना किया हमने लगाए 3 बार्स और यूज़ किया 12 mm डाया बार जिसके एक का एरिया है इतना 113.04 सो मैंने AST प्रोवाइड किया 339.12 mm स्क्वायर हालांकि ज़रूरत कितना था 279.14 इतना मैंने प्रोवाइड किया ठीक है इट्स फाइन नाउ लेट्स कैलकुलेट द स्पेसिंग राइट लेट्स कैलकुलेट द स्पेसिंग स्पेसिंग कितनी बनती है बार्स में area of one bar divided by AST that we have provided multiplied by 1000 which is the breadth So this is 113.04, provide हमने किया 339.12 multiplied by 1000. By calculations, it is 333.33 mm. This is the spacing. So therefore I'll provide 3 bars of 12 mm dia. I'll provide 3 bars of 12 mm dia at the rate of 300 mm, center to center spacing along length. So this is my longitudinal reinforcement. All right, students, this is my longitudinal reinforcement. So longitudinal reinforcement के लिए I have provided 3 bars of 12 mm dia at the rate of 300 mm center to center spacing along the longest span, that is length. And for the main reinforcement, I provided 10 bars of 12 mm dia at the rate of 100 mm center to center spacing along short span. So along short span, there was my main reinforcement, or there is my main reinforcement, and along the longest span there is my longitudinal reinforcement. And for longitudinal reinforcement, I provided 3 bars of 12 mm dia at a rate of 300 mm center to center spacing. And for my main reinforcement, I provided 10 bars of 12 mm dia at the rate of 100 mm center to center along shorter span. इसके बाद स्लैब में बचता क्या है? डिस्ट्रीब्यूशन स्टील, या डिस्ट्रीब्यूटर्स भी जिनको बोलते हैं, distribution steel calculate करना है. This was my main. Now distribution steel. And distribution steel is 0.12% of gross area. Alright? Distribution steel provide करते हैं हम 0.12% of the gross area. यहाँ पे हम gross area लेंगे स्लैब का और कैलकुलेट करेंगे अपना distribution steel, या जिसको distributors भी बोलते हैं. Distribution steel is also known as distributors. Alright? Now, how much is the AST distribution steel required in our case? It is 0.12%, 0.12 divided by 100 multiplied by the gross area, जिसके लिए हम डिज़ाइन कर रहे हैं. breadth into depth, breadth है 1000, depth हमने ली है 200, तो ये बनता है 240 mm square. So distribution steel का जो एरिया है वो मुझे लेना है 240 mm square. अब देखते हैं कैसे क्या लगाएंगे और कैसे प्रोवाइड करेंगे, क्या स्पेसिंग वगैरह. लेट्स सी दैट. Alright, so I'll be using 8 mm dia bars along for distribution steel. So area of one bar is pi by 4 into this, which is 50.24 mm square. Alright, number of bars, कितने number of bars लगेंगे, एरिया कितना है ज़रूरत, 240 mm square. एक बार का एरिया 50.24, which is equal to 4.77. Let's go 5 bars. तो AST provide कितना किया मैंने, 5 multiplied by 50.24, which is 251.2 mm square as per the calculations. वो spacing क्या रखेंगे इनके दरमियान? Spacing हम provide करेंगे 50.24 divided by 251. This is area of 1 bar. This is AST provided, multiplied by 1000, which by calculations is 200 mm. So provide 5 bars of 8 mm dia. Provide 5 bars of 8 mm dia at the rate of 200 mm center to center as distribution steel or distributors. So these 5 bars of 8 mm dia which have been placed at 20 mm center to center spacing are my distributors or distribution steel. Alright, so हमने main reinforcement भी calculate की, longitudinal reinforcement भी calculate की और distribution steel भी calculate किया, and this is how I design my deck slab in case of this steel trussed bridge. Alright, so deck slabs ऐसे ही design किए जाते हैं. We have to calculate the moments along the shorter as well as along the longer spans by both dead load as well as the live load. Live load इस केस में जो हम स्टील ट्रस ब्रिज डिज़ाइन कर रहे हैं, इस केस में लाइव लोड कहाँ से लेंगे? ऑलरेडी दिया था कि आपको यूज़ करना है IRC क्लास AA की ट्रैक्ट व्हीकल के लिए, तो उसके हिसाब से हमने लिया, उसके हिसाब से हमने अपने जो मोमेंट कोफिशिएंट्स है उनको ले लिया. मोमेंट कोफिशिएंट्स लेने के बाद हमने बेंडिंग मोमेंट्स कैलकुलेट की. We use the Piaget's curves to find the moment coefficients M1 and M2. उसके बाद I calculated my bending moments along the shorter span and along the longer span by the live loads which were the IRC class A tracked vehicle loads. उसके बाद मुझे अपने bending moments मिल गए along breadth and along length. On the same lines and by using the same Piaget's theory, I calculated my bending moments by dead load along both the spans, the shorter span and the longer span. Then I summed up the two to calculate my design moments. Design moment along the breadth was bending moment due to live load plus bending moment due to dead load. And on the same lines, my bending moment, my design bending moment along the longer span was the summation of the that caused by the dead load as then by cause the live loads. डेड और लाइव लोड्स को सम किया तो मेरे डिज़ाइन मोमेंट्स बन गए along both the spans. उसके बाद मेरे पास इलास्टिक डिज़ाइन कोफिशिएंट्स थे. उसके बाद मैंने ये भी चेक किया कि जितनी मैंने इफेक्टिव डेप्थ प्रोवाइड की है क्या वो सेफ है कि नहीं. उसके बाद मैंने अपना निकाला रीइंफोर्समेंट डिटेल्स क्या देंगी अब अपने स्लैब को, बोथ along the shorter span and along the longer span. Shorter span is the main reinforcement, along the longer span is my longitudinal reinforcement. उसके लिए भी क्या प्रोवाइड करना है वो वगैरह हमने सब डिज़ाइन कर रखा. आखिर में डिस्ट्रीब्यूशन स्टील क्या लगाएंगे वो भी डिज़ाइन करके रखा. डिस्ट्रीब्यूशन स्टील इज टेकन एज 0.12% ऑफ द ग्रॉस एरिया. ग्रॉस एरिया मैंने लिया, उसका 0.12% जितना बनता था उसके हिसाब से मैंने अपना डिस्ट्रीब्यूशन स्टील भी कैलकुलेट किया और मैंने प्रोवाइड किए 5 bars of 8 mm dia at the rate of 20 mm center to center spacing as distribution steel. So all the three things are covered: my main reinforcement, my longitudinal reinforcement and my distribution steel as well.